Hi, thanks for joining me today. I've got a fun number theory problem from the PAMO 2019. We have k a positive integer, and we want to consider k not necessarily distinct prime numbers, such that their product is 10 times their sum. We want to know what are these primes and what is the value of k. So k here isn't an arbitrary positive integer, it's unique, supposedly, according to the question. And we want to find that value of k, and there's only one set of prime numbers, of which there are k, such that their product is 10 times their sum. Anyway, if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to dive straight into a solution. Okay, so like with most prime number problems which involve prime factors of numbers, we're going to start by labeling our prime factors in the pretty standard way: P1, P2, P3, and so on, all the way up to Pk. And now, well, although we don't know what these primes are, we can prescribe an order here. We can say that P1 is less than or equal to P2, is less than or equal to P3, and so on, all the way up to Pk, which will be our biggest prime here. And notice that I'm putting less than or equal to signs as opposed to just less than signs, because of course these primes are not necessarily distinct. There could be repetitions here. Cool. So we have this here, and well, we can use the other fact in the question, which is obviously going to be important, that the product is 10 times their sum. So the product of the pi's, so the product from I equals 1 to k of pi, is 10 times the sum from I equals 1 to k of pi. Cool. The product is 10 times the sum. Well, immediately we notice this right-hand side here is a multiple of 10, and so that tells us that the left-hand side must also be a multiple of 10, and therefore two of the prime factors must be 2 and 5. So two of these pi's, one is 2 and one is 5. There could be other 2's and other 5's as well, because there could be repetitions here, but we know that there's at least one 2 and at least one 5 on the left-hand side. And since we've prescribed this order here, and 2 is the smallest prime number, we can with confidence say that P1 must equal 2. Now, annoyingly, we can't quite say that P2 is 5 or P3 is 5 or guarantee what the index is of the prime number, which is 5, because it could be that P2 is 5, or maybe P2 is 3, in which case maybe P3 is 5, but even then, 5 doesn't necessarily have to be one of those two. It could be later down the list. If, let's say, P1, P2, and P3, they could all be 2, for example, and then maybe P4 is 3, and then maybe P5 is 5. So we don't quite know which one is 5, but we can say that it's somewhere. So we may as well say PL equals 5. And obviously L has to be somewhere between 2 and K. Okay, awesome. P1 is 2, PL is 5, and we get this here. So using that, we may as well divide both sides by 10. So obviously on the right-hand side, that just gets rid of the 10. So you get the sum from I equals 1 to k of pi. And on the left-hand side, well, we've got the product from I equals 1 to k of pi, but I'm dividing by 10, so I can strip off the 2 and the 5, and so that's going to give me the product from I equals 2 to k, but obviously I have to exclude the lth prime, which would be 5. And I get this result here. The product from I equals 2 to k without I equaling L of pi is the sum from I equals 1 to k of pi. But I can do a little bit more on this right-hand side. I can use these two facts again and strip those two terms out of the sum. And obviously 2 plus 5 is 7, so I can get this as 7 plus the sum from I equals 2 to k, again, I not equaling L of the pi's. Awesome. So I've got that this product here is equal to 7 plus this sum here. But now I'm going to put an upper bound on this right-hand side. I'll keep the 7 there, and I want to think about this sum. What can I say about pi? Well, each of the pi's are one of these numbers in this list, and all of them are less than or equal to this biggest prime here, pk, or biggest prime in the question. And what I can say, therefore, is all of these pi's are less than or equal to pk. And well, how many terms have I got in the sum? Well, I'm going from 2 to k, so that would be k minus 1 terms, but obviously I'm excluding the lth term, so that's going to be k minus 2 terms. So therefore, I can say that this is less than or equal to 7 plus k minus 2 lots of pk. Amazing. So I've got that this product here is less than or equal to 7 plus k minus 2 lots of pk. Let me clear up the screen and we'll continue. Okay, so what can we do with this inequality? We can't really simplify it much more, but we do start to see why k is probably unique, or maybe something slightly less strong. We can see why k is probably bounded. K can't be too big, because this left-hand side here grows exponentially. It's the product of k things, or of order k things, and this right-hand side here only grows linearly in terms of this k here. So what we're going to do is use that to our advantage to see if we can maybe make this a bit more concrete and show that this left-hand side will eventually grow to be much faster than this right-hand side, and so this inequality can't hold for k being too big, and we'll get that k must be just a bounded number. We'll only have a few cases to check. So what I'm going to do is divide both sides by pk here, and in doing so, the right-hand side here just becomes 7 over pk plus k minus 2. And this right-hand side here is going to be the product from I equals 2 to k minus 1 of I not equaling L of pi. Cool. Okay, so this right-hand side is that. We're not going to touch that for the time being. Let's think about this left-hand side. I want to provide a lower bound for that. Well, I know that each of these pi's are going to be at least 2, because 2 is the smallest prime number. Okay, and well, we can think about how many numbers there are in this product. Well, we're going from 2 to k minus 1, so that's going to be, well, k minus 2 terms, but I'm excluding I equaling L, so that's going to be k minus 3 terms. However, we've got to be a bit careful here, because it could be that k equals L, because if you remember, P1 was 2 and PL was 5, and we said that L had to be some number between 2 and k. And if it is the case that L equals k, then in fact we only have k minus 2 terms here. But in fact, that means this inequality here is still true. It just means that if k does equal L, we could actually make this a bit stronger and put this as k minus 2, 2 to the k minus 2. But we're going to keep it to be true in all cases, so we're going to keep this as 2 to the k minus 3. However, yeah, it is definitely worth being careful when you have things not in your product here. But yeah, that only would mean that we could actually make this a stronger lower bound. But we'll keep it as 2 to the k minus 3, and we can say that that is less than 7 over pk plus k minus 2. Well, what about this pk here? Well, we know that pk, which remember is our biggest prime, has to be at least 5, because we know that 5 is one of our primes, so pk is going to be at least 5. So this is going to be at least 7 over 5, which is 1.4. So I can say that this is less than or equal to 1.4 plus k minus 2, and that's obviously going to be less than 2 plus k minus 2, which is obviously k. And so 2 to the k minus 3 is less than k, and so 2 to the k minus 3 I can with confidence say is less than or equal to k minus 1. And we get a much more obvious inequality here, where we can say that this is going to cause some issues if k is large. If k is 10 here, on the left hand side we have 2 to the 7, which I think is 128, and on the right hand side we have 10 minus 1, which is 9, and 128 is definitely not less than or equal to 9. This guy here is only true for a few values of k, and it's not too difficult to see that for this to be true, well, firstly, k has to be at least 2, which is interesting, because otherwise this right-hand side would be 0, or a negative number, and obviously 2 to the power of anything has to be positive, but also k can't be too large, so maybe k has to be 2, 3, 4, or 5, and we can see when we plug in k as 5, we get 2 to the 5 minus 3, that's going to be 2 squared is 4, is less than or equal to 5 minus 1, which is 4. So that just about holds there. And if you try k as 6, you'll get 2 to the 3, which is 8, is less than or equal to 5, which is obviously not true. And so yeah, this is only going to work potentially for 2, 3, 4, and 5, but in fact we'll be able to eliminate some more of these values here and narrow it down to 1. And in fact, immediately I noticed that in fact 2 won't work either, because if I plug in k as 2, I get 2 minus 1 is 1. If k was 2, we can actually just go back here. That means we have 2 primes, so those 2 primes have to be 2 and 5, and so we get 2 times 5 equals 10 times 2 plus 5, and obviously that's just not true, and so we can get rid of 2 here. Anyway, let's have a deeper inspection on 3, 4, and 5, and narrow it down to one value of k, and hopefully then we can work out the primes as well. Okay, so k is either 3, 4, or 5. Let's eliminate 3. This is actually quite easy to do. Suppose we could have k as 3. So let's call those, the 3 prime numbers. One will have to be 2, one will have to be 5. Let's call the third one p. So we have 2 times 5 times p is equal to 10 times 7 plus p. But this simplifies to p equals 7 plus p. And that obviously has no solutions. So k can't be 3. Great. So k is either equal to 4 or 5. And it turns out that k must be 4. So to prove that, let's first eliminate 5. Let's imagine we could do it with 5 and use a similar argument, just requires a bit more work here. Let's call the 3 remaining primes p, q, and r, and again we'll have them in this non-decreasing order. So we can say that p, q, r is 7 plus p plus q plus r. Cool. Let's now divide by r here, which is supposedly which is our biggest prime number. So we get pq is equal to 7 over r plus p over r plus q over r plus 1. And let's think about an upper bound for this right-hand side. Well, because r is the biggest prime, we know p and q are smaller than r, so p over r and q over r will each be less than or equal to 1. So I can say this is less than or equal to 7 over r plus 3. And remember, r is a prime number, so it's at least 2. So 7 over r is going to be at most 3.5. So adding 3 to that is going to be 6.5. And so we get that pq, which is obviously a positive integer, has to be less than or equal to 6. Okay, so we've got two prime numbers multiplying together, and their product is less than or equal to 6. And so that tells us that either p must therefore be 2. P can't be bigger than 2. Because p is the smallest of the primes, so if p was bigger than 2, it'd have to be at least 3, but then q would be at least 3, and 3 times 3 is already 9. So p must be 2, and then q either equals 2 or 3. We don't know. One of the two. And you can actually just check both of these cases here. Maybe I'll do p equals 2 and q equals 2 quickly and show that that just doesn't work. If you substitute that back in over here, you get 2 times 2 times r, so 4r equals 7 plus 2 plus 2, which is 4 plus r, and so you get 4r equals 11 plus r, and you get 3r equals 11, and that obviously doesn't work. And yeah, let's just do p equals 2 and q equals 3. Again, subbing that in up here, you get 6r equals 7 plus 5 plus r, so you get 6r is 11 plus r, and so you get 5r equals 11, and of course that has no prime number solution for r. Amazing, so that eliminates the possibility of k being 5, and so we've proved that k must be 4, but we still have to check that it does work, and so we need to find 4 prime numbers that multiply to give us 10 times the sum of those 4 prime numbers. Okay, so let's dive into k equaling 4. Again, we'll call the remaining 2 primes, let's call them p and q, and again, without loss of generality, p will be less than or equal to q. And what can we say? We can say that p times q must be equal to 7 plus p plus q. Let's bring these p and q's onto the left side here. So pq minus p minus q equals 7. And here's a really, really nice trick. What we're going to do is add 1 to both sides, which might seem pretty random. But the reason we do that is because now this left-hand side factorizes really, really nicely. This is just going to be p minus 1 times q minus 1. And that's why we added the 1 there. So we could factorize it like this. So if you've not seen this trick before, I mean, you can just check for yourself this works just by expanding the brackets here. You will get exactly this. But this is a really useful trick, so be on the lookout for things factorizing like this. And now this is great because we know p and q are prime numbers. In particular, they're positive integers at least 2. So we've got p minus 1 and q minus 1 are going to be positive integers. 2 positive integers multiply to give us 8. There's only a few possibilities here. So either we could have that p minus 1 is 1 and q minus 1 is 8. That's one possibility. Or we could have p minus 1 is 2 and q minus 1 is 4, because those are the only factors of 8. And of course, you've got to remember that p must be less than or equal to q, so we can't have p minus 1 being 4 and q minus 1 being 2, for example. So there's only 2 possibilities here. Let's look at this first guy. What does this give us? Well, that tells us that p is 2 and q is 9. Uh-oh, this doesn't work because that's not a prime number. So this doesn't work. What about this second one? We get p equaling 3 and q equaling 5. And those both are prime numbers, so this should work. And so we can just check. So if we get our other prime numbers 2 and 5 back in, so our 4 prime numbers should be 2, 3, 5 and 5. If we multiply them together, what do we get? We get 160. That's if we multiply them. And what if we add them up? 5 plus 5 is 10, plus 3 plus 2 is 15. Sorry, that's supposed to be 150. I mismultiplied them. 5 times 5 is 25, times 3 is 75, times 2 is 150. If I add them up, I get 15, and obviously then if I multiply that by 10, I get 150. And so this works. And this is our unique solution here. So the 4 primes are 2, 3, 5, and 5, and k is 4. A really interesting number theory problem where the technique is to kind of, make k not any kind of positive integer, narrow it down to a few potential values, then narrow it down to 1. And then once you've got what k is, that's kind of one less unknown in the question, and you can then work out what the prime numbers have to be. A really interesting problem. If you are new to the channel, please do consider subscribing and giving this video a thumbs up if you have enjoyed it. Thank you for watching. I'll catch you in the next one. Have a great day.